Our next speaker, we'll get to hear from the 2024 Edith and Peter O'Donnell Award recipient in Technology Innovation. Last night we saw a video from Dr. Kimberly Hambuchen, who is the Deputy Chief of Software, Robotics, and Simulation at NASA's Lyndon B. Johnson Space Center. After she finishes her talk, we'll have time for questions. Dr. Hambuchen?
All right. Am I live? Okay. Good morning, everyone. I am really excited to get to talk about the work that I was nominated for the O'Donnell Award. And I feel like I just lucked into the fact that the theme this year was AI and machine learning because I work in robotics. We like to use a lot of AI and machine learning with our systems. And so it fits right in. And I also feel like I've got my people here this morning. So each of the presenters, I recognized their work and was really excited that I get to be involved with these people. So this is my pointer. I don't really know how to use this. There we go. OK. So what I'm going to talk about this morning, and I'm going to try to stay on time. It's difficult when you have lots of robots that I would really like to discuss. But I'm going to talk about remotely operating robots for space exploration. That's really where I've focused my career since I came to NASA. And it's interesting, I worked on developing cognitive structures and systems for robotics in grad school. And then when I came to NASA, realized, well, we kind of need to make things work. So I moved into an application space instead of doing real research. And really, what my focus in my career has been on is how are we going to operate complex robots in space when they are not surrounded by people to tell them what to do. And we've got these three really difficult constraints that we're working with in space that terrestrial applications, for the most part, don't have. Number one, we have time delays that are very large, that people who work in terrestrial robotics would think, they think large time delays are 100 milliseconds. But we're talking about, with Mars, it's between 7 minutes and 42 minutes round trip from when you send data to something on Mars and you get the data back. So, and then we also have really limited bandwidth. We're not going to have gigabit Ethernet to talk to the gateway system that Vanessa discussed yesterday. We'll have limited bandwidth, which means you've got to be really careful about what data you're sending from a robot to a ground operator, what data you're sending back to the robot. And then our third constraint, and hopefully this is going to be changing soon in the future, near future, is that we have limited processing power to work with on these robots. For instance, Vanessa spoke briefly about the Viper rover that we are currently integrating at Johnson Space Center. And I believe it's using a RAD 750 processor, which will not, my Apple Watch is better than that. So a lot of the really intense processing that you need to do for some machine learning type applications cannot be done on those types of processors. We do have folks working on better radiation hardened processing, but 10 years ago, I heard it was right around the corner, and I'm still hearing it's right around the corner. So we'll see how that really goes. So we've got those three constraints that we're dealing with. And the other thing is that we're envisioning a whole bunch of different robots working together in a distributed environment. So back to this picture. This is our family picture that you may have seen last night. And these are all different prototypes that we've built within my robotics group at JSC. And so you can see you've got humanoids, you've got a spider robot, you've got big rovers, you've got small rovers. So we really would like to have this complex group of robotics working together on planetary surfaces, and right now really focused on the moon. But how do you operate all of these robots? So for those who don't know in the room, robots aren't going to take over the world anytime soon. They are still pretty stupid. You can watch Boston Dynamics videos all day long, but then you also need to go watch the videos they put up of when it fails miserably at what it was supposed to do. And we're still trying to figure out how to actually integrate machine learning and artificial intelligence into robotics, because it's different when you move from data in a computer to an actual embodied thing that is moving around and interacting with the world. So when I started at NASA, I was asked to work on this project that was looking at how to operate a humanoid robot over time delay. Nothing's moving. There we go. And so I came in, I'm working with this group of really smart people, and one of the ways that we operated our original Robonaut humanoid is through telepresence. So this was back in the day. I think it says 2006 on that publication. And Mike Goza is wearing like a $35,000 VR helmet. He's got several other sensors on him, and all the motions he does, the robot copies. And so he's basically, the robot's his avatar. The robot is his avatar. We really wanted to figure out how to operate this type of robot with a small time delay. Is this something we could operate on the moon with a person on the ground in this manner? Because we still were not, and we still aren't, able to have fully autonomous humanoids that are doing exactly what they need to do. So with this project, we actually were putting, Mike was operating a virtual Robonaut avatar, and we were predicting Mike's movements with this virtual avatar. So we were predicting the intent of Mike's movements. And this was really interesting, but you can see we have a very simple setup. It worked out quite well, and the robot was able to, we were able to tell the Robonaut that we're predicting that Mike's gonna go grab this specific handrail, and so the robot would go ahead and start that motion, trying to mitigate some of the time delay that we thought we were gonna see between robot and operator. And it was quite successful, but it was really, really kind of research-oriented work. And that's when I kind of learned that this is gonna be very difficult operating these really complex robots over time delays. So then I was asked to participate, or moved into, a group that was working on a new human scale, or human rover, the space exploration vehicle. And this was something built for humans to drive, but we also piled a bunch of sensors on it so it could be a large robot that could be driven remotely or autonomously when people were not in it. And it's the type of, we're actually looking at building these types of things for our Artemis mission that's coming up. So we wanted to figure out if we could mitigate the time delay again with the operation of this type of rover. And what you see is a very rudimentary interface that I wrote. And we developed this method called Predictive Interactive Graphical Interface, calling it PIGGY for short. And it allows a human operator who would be on Earth to go ahead and plan out a path that it wants this rover to take, allow the rover to make its own decisions, to do its own path planning, if you will. And you can see where the rover's diverging off of the plan that the operator had sent, because you can predict that certain things in the terrain might be making the rover go somewhere different, and maybe they're getting off course, maybe they're getting close to a crater. And I'd also like to say this is before Velodyne sensors, so we still had some pretty limited sensing on the vehicle, because now this would all be a very different story, but this was, what, back in 2009. So I'm now finding out how different ways to operate mobile robots over time delays. And then I was asked, let's see, there we go, to make a Robonaut 2 on a mobile base, which we call Centaur 2, go collect science samples out in the desert in Arizona where we were simulating operations on the lunar surface. So this one was really interesting. I had the piggy that I could work with for telling it where to go on the wheels, but the intent prediction wasn't going to be very useful for picking up unknown objects in an unknown environment. So that's a lot more useful when you're in, say, an International Space Station that you have a full model of and you know where everything is. So we developed this not very effective method using kind of some triangulation between depth images. And it really showed that we had a problem in how we were operating these robots because nothing that we had been doing was efficient. It would take a whole lot of time to use the methods that we were using. And then came along, to follow after Chris, the DARPA Robotics Challenge. So we participated in the DARPA Robotics Challenge, which was a challenge that really, I believe, was designed to kind of advance humanoid robotics. What it did was really advance how we operate complex robots. So I'll let you read all of that, but this was a 15-month from design starts until we go do our competition with a whole bunch of other people. And we decided to build a bipedal humanoid. And we had to do 5 tasks. And each of those tasks has an object that it needs to work with to execute the task. And so the other thing we did with this was we decided we were going to use something called ROS, the Robot Operating System. That is an open source framework and set of tools that if you build your robot to basically use ROS, then anything that people put online, open source, you can use. Changed the game for me, because I was back in grad school writing candy edge detectors, just to get some computer vision work done. So because we decided to use ROS, we now had a whole suite of tools that were open to us. And while going through this 15-month design and operation, affordance templates were born. So affordance templates is just a really fancy Ph.D. type word for a task execution template. It's really about telling the robot, here is where you need to put your end effector or your foot or something in order to interact with the object to complete the task. And I just got reminded of me talking in that video last night. So the affordance template ROS package was developed. This changed the way we were operating the robot, allowed us to actually more quickly get things done, and really give the robot some good information on how to complete these tasks. So this is the best video I could find to show you what it really looks like. So this is a simulation of a robot, and it's got sensors, and it's collecting sensor data, so it's creating a depth map of its area. And if you're a human operator, you can see there's a ladder. You can see there's stairs. So affordance templates allow you to create a template that shows the robot how to walk up the stairs. So we don't have to have a very fancy machine learning algorithm to teach the robot how to walk up the stairs. We just say, here's where you place your feet to walk up the stairs. You can do the same thing with the ladder. Here's where which we never even attempted to climb a ladder, but here's where you place your feet and your hands to climb up a ladder. So we did a similar thing with, there was a task to close a valve. We didn't know what the valve was going to look like, but we created different templates of valves and showed the robot, here's how you have to move your hands, your end effectors, to close the valve. Here's what you have to do to open the valve. So it really, it changed the game for us at NASA. And I'm sad to say that we did quite poorly at the DARPA Robotics Challenge, but this was kind of, this and then the Valkyrie robot were two of the best things to come out of placing very poorly in that challenge. So after we did poorly and I got over it, I was asked for some help with Robonaut 2 operations. Is that moving? There we go, okay. While we were doing the DARPA Robotics Challenge, there was another group that was actually designing climbing legs for Robonaut 2, which had been sent to the International Space Station. And they had sent the legs up to the International Space Station. An astronaut was going to do some robot surgery on the station. And the group that was doing this really didn't have a good way to do operations for Robonaut. And so I said, why don't I just go ahead and port affordance templates to your robot? Because it was designed to be generic so that it could be infused into any robotic system that's using ROS. And oh, I have several videos on this. Just click through them all. So once we did that, all of a sudden, changed the game for the Robonaut team. They were able to, there we go. I have 4 videos. There we go. So they were able to much more easily operate this robot. They had several demonstrations they needed to get through. And by the way, this is in our active response gravity offload system in our large building at JSC. So we were able to do demonstrations of how it would be on space station. We were able to offload the robot to 0 microgravity. But this was, really, this is when I kind of saw the real effect of what this technology was going to have. And so after I was able to do that, other people started taking my work and using it. This is actually a video of some robotic systems doing high-level task planning, and they just assumed that they would use affordance templates to do the task execution. So it started becoming ingrained into the work that people do. And then, there we go. We actually started working with a company called Woodside Energy in Perth, Australia. We have a Space Act agreement with them. They did have a Robonaut, now they have a Valkyrie on site in Australia, and they wanted to start using affordance templates because they realized this was easy to program, easy to use, and they're very interested in having unmanned rigs, taking people out of the very dangerous parts of their environment. And then we started working with the Irregular Warfare Technical Support Directorate in DoD, used to be CTTSO. They were really interested in how a humanoid-type robot could help in looking for potential bombs, diffusing bombs. And we had some operators of bomb disposal robots, and they saw affordance templates, and they were like, well, how do we get that on our robots? So that was really exciting for me to see people get excited about technology that I had created. I will say, I have so many robot videos, but not enough time. I tried my hardest to get affordance templates on the International Space Station robotic manipulator. And after doing a rotation at International Space Station, I realized why I was never going to make that happen. It's very difficult. They are stuck in their ways. But we did some testing. And then lastly, we found that people have actually taken the affordance template work and expanded on it. So Craftsman is a product from Track Labs in Houston that is based on affordance templates, and they are actually selling it to industrial operators and have licensed it. And then Woodside has collaborated with us to actually start putting some machine learning into the affordance templates themselves to start moving towards more autonomy. So that is my talk. Thank you very much. It's me and my robot family. This has been an absolute pleasure and really exciting to come speak to you all today. Mm-hmm.
We have time for a few questions.
Christine Economides, University of Houston. So there was C3PO, and there was R2D2. And as I recall, R2D2 was the smart one, And C3PO was the stupid one that acts like people. And it just strikes me that if you have environments where you rather people don't go, and don't put ladders in them. If robots are going to go there, design the environment for the robot. So do you think like this at all? I'm just kind of shocked to see robots trying to turn valves and stuff like this.
Well, so for the DARPA Robotics Challenge was after Fukushima, the robots that they had sent into the disaster area couldn't get into much of anything. And so there was interest in, can these humanoids maybe do that? And as you know, Robin told you, that's not really what we need. But for us at NASA, you would think we could say, let's build the environment to allow robotic systems to do things easily and be more practical. But we don't always get that out of the people who are developing the systems, the people who have the money for the programs, because there is a lot of heritage at NASA. And they want to use heritage technology because it's cheap. And heritage technology was built only for humans. For instance, there is, we have cargo transfer bags called CTBs. They're the white bags that everything gets put into to get delivered to space station. They are all white. The handle is white. The zipper is white. So for a robot, it's like, ooh, that's really kind of difficult to figure out where the handle is. If you just make the handle red or blue or black, that would make things so much easier. So those are the sorts of things we're trying to work with our program partners at NASA on. Like, how can we just do little things to make it easier? But we're still going to have humans in our environment. So that's...
Well, if you go far enough, you might
True.
be better off not trying to make it for humans.
True.
This cohabitation between robots and humans is kind of weird. Sorry.
Well, I look at it as they're another crew member that we don't have to feed, we don't have to carry water for, they don't need to breathe the air. And you know, I am focused on human exploration missions at JSC because that's really our charter down there. And you know, I don't know when we're actually going to have robots and humans working together in space. I mean, we kind of do with Space Station Arm. The astronauts kind of they have to operate that themselves sometimes in certain scenarios. But you know, I'd really love to see some sort of small little manipulator or dual manipulator who's assisting astronauts on board a space station doing utilization tasks, because crew time is very, very expensive and very hard to come by. They spend a lot of time fixing things up there. So, any other questions? I can't see.
Okay, let's thank Dr. Hambuchen, please.
All right. Oh, look at me.
Thank you very much.
Thank you.
Appreciate it.